For this set of slides, what I'll do is I'll introduce adversarial search. So here it's actually not so much about reinforcement learning, but this will provide some background for two-player games where there's some adversaries. Okay, so I'll explain some classical work on minimax search, evaluation functions, as well as alpha-beta pruning. So these were in fact some of the traditional approaches for solving games like chess, as well as Go, and most two-player games. Okay, so solving a game is challenging, and perhaps the main challenge here is that we have an opponent. So in the way we've defined reinforcement learning, we said that what happens is that there's an agent and then there's the environment. But the reality here is that in two-player games, the environment is really another player. And this could be problematic because the other player is malicious, unlike the environment where we said, oh, the environment will essentially just determine what next state we end up in, and perhaps is going to follow some distribution for that. When we talk about an opponent, the opponent might not just sample a state at random. It will have a policy, and perhaps this policy will simply try to do what might be the worst for the agent, right? Because the opponent is trying to defeat the agent. So here we should really approach the problem differently, and at least traditionally it was framed differently because then we were really treating the opponent as another agent. So we had two agents, so the environment was really the same as the main agent, but trying to do the opposite. Okay, so one way of modeling this is to in fact construct a search tree. So historically, these games were solved by doing a search. In other words, by simulating what would happen if we were going to execute different sequences of moves. And then in doing this simulation, we would have one player that simply tries to maximize a score, and then the opponent would try to do the opposite, so it tried to minimize the score. So obviously here, this is in a case where there's a single score, and then you could frame the game as saying that, one player is trying to get the highest score possible, and then the other player is trying to minimize that score. In most games, it's actually framed in a way where both players have their own scores, right? So they're both trying to maximize their own scores, but in most games what happens is that if one player increases his or her score, that chances are that's going to decrease the score of the other player, right? So in situations where it's symmetric like that, then you could have a single score, and in fact this would be known in game theory as a zero-sum game. Okay, so that's the type of game that we're going to look at, and let's get straight into some example. So let's say that we want to play tic-tac-toe. Okay, so very simple game. We're putting some X and O's throughout, and then the goal here is to form a line, which could be a horizontal, vertical, or diagonal line in order to win, right? And then so here we can frame the game as saying that initially there's a player. Let's say that is the player that we call Max. This player will put down an X, and then it can put down an X in any position, right? So then we would have 9 possible moves. Then after that, it's going to be Min's turn. So Min will put down an O, and then it can put it again anywhere. But now you see if we just consider this move, then there will be 8 further moves for the 8 remaining locations of the O. And then we keep on going. Then after that, it's Max's turn. Max will put down an X. These are possible moves after this one, and so on. And then at the very end, we end up with either a situation where one player wins, or actually here would be, in the case of X, so this would be the case where X loses and therefore would earn a utility of -1. Or we could end up in a situation where everything is filled up but nobody wins, so it's a draw. The score is 0. Or we could have a diagonal here where X wins and then earns +1. Okay, so at least a very simple approach that conceptually will work but might be intractable, in fact most of the time will be intractable, is to build the search tree like this all the way till the end of the game. Then we can assign the final score and then back propagate this. Okay, so back up the values simply by taking the min, the max, the min, the max at every node according to whose turn it is to play. Right? And in doing this, we'll ensure that we're going to find a policy that's going to yield a good strategy. In fact, the best strategy possible, assuming that the opponent is also the strongest opponent possible. Okay, so yeah, so here we want to find an optimal strategy, and then it's going to be the one that leads to outcomes that are at least as good as any other strategy, given that min is also playing optimally. So here it's possible, like in real life, when you play against someone else, that opponent is not necessarily optimal, right? So in fact, it might be a friend of yours, and you might know the weaknesses of your friend when your friend plays this game, and you might be able to exploit that, but at least here, ideally, right, if we want to have a strategy that is optimal and will work against any player, right, then it should be a strategy that will work against whatever is the optimal strategy as well, and that's what we would define as the optimal strategy. So here you see it's a little bit weird because to define the optimal strategy, we need to have an opponent that we know is optimal, and then there's a question of, well, what is the optimal strategy for that player? And then we could define it as, well, that's a strategy that's optimal with respect to another optimal player, and so on. So it's a recursive definition, but in any case, that's the way it is. And that suggests that really at the end, we've got some sort of equilibrium, right? So one strategy is going to be optimal with respect to another one if the other one is also optimal with respect to the first one, right? So in game theory, often there's this notion of best response, where what you want to do when there's an opponent is to select your moves in a way that would be best given what the other player is going to play. And then this here is not going to be stable unless both players are selecting a best response with respect to the other player's strategy. And then at that point, you know, there's something stable, there's an equilibrium, and that's typically what you would expect would emerge. Okay, so in game theory, we can study all kinds of properties for when such equilibria would arise and how to obtain them. But now, in particular, this type of game that I'm describing is known as a zero-sum game, because here, if I have a single score and then max is trying to maximize and min is trying to minimize, it means that if, let's say, we start with a score of 0, whenever one player does something good, let's say improves the score and gets something positive, then it really means that the other player is losing by the same amount. Okay, and vice versa. So you could say that if we had 2 scores for the 2 players, then their sum would be 0, because whatever gain one player gets would be cancelled by a loss from the other player. Okay, so that's a specific type of game, and here we're considering, in fact, what are known as zero-sum game with perfect information, because in Tic-Tac-Toe, or otherwise chess, or otherwise Go, in many board games like this, then the board configuration gives you all the information that you need. So there's perfect information, so that means it's fully observable. Now we just discussed some video games or some other games where it might be partially observable, so this would be cases where there's imperfect information, but what I'm going to talk about for now is just the case with perfect information. Okay, any questions so far? Okay, good. So that should not be too hard. All right, so now what I described earlier with Tic-Tac-Toe, we can formulate an algorithm that's known as the Minimax algorithm. And what it does is essentially build a search tree, as we saw before, all the way down to the end. And then at the end, we're going to have some leaves with some values. And then we simply want to back up those values by either taking the max whenever we are in a max node and taking a min whenever we're in a min node. So yeah, this is called minimax search because we're alternating between min and max. And then the idea is that if we are in a max node, then the action that we would select would correspond to the move that would give us the maximum value. And then if it's the opponent's turn, then the opponent is going to minimize and therefore select an action that's going to correspond to the move that minimizes the score. Yeah, so then we can essentially solve the game or find an optimal policy by computing like this, start in a bottom-up fashion, all the values alternating between min and max. Okay, so here's some pseudocode that does that. Very simple. Again, we have here what we do whenever we have a max node. This is a min node, and then this is wrapped up here into an overall minimax procedure. Okay. Now this algorithm will do the job, but there's an interesting question about the complexity. So here, can anybody suggest what might be the time complexity of essentially solving this game by constructing a minimax search tree as I described it? Yeah, so it's going to be exponential. Exponential in what? Right, so here we have to look at some properties of our tree, right? So this tree is obviously going to grow exponentially, and it's going to be exponential in the height or otherwise the depth of the tree. And then this exponential is going to be on top of a base, right? And then the basis is essentially going to be the branching factor for each node. So here we could say that for the search tree, at any point in time, a player will have a number of possible moves that will determine the branching factor. And then the length of the game, which is a number of moves, will determine the depth of the tree. Okay, and then in general, we're going to call apply, which will be one alternation of one player followed by the next player. Right? So whenever both players take a turn in selecting a move, we're going to call that apply. Okay, so then, yeah, the time complexity here is going to be exponential. I'm going to use B for the branching factor, D for the depth, and it's generally exponential in the depth. Okay, now for space complexity, it's actually a little bit better. So here, yeah, can anybody guess how complex or how much memory this algorithm for doing minimax search will need to work accurately? So let's just go back. Again, this is our search tree, right? So if you want to solve this, right, there's obviously many ways in which we could order the operations, right? But what's an effective way to do this to reduce memory? Yeah. Or you're not sure? Okay. Kira?
Well, if we did it completely depth first, then we would only need to look at B terminal nodes at a time and then all the ones leading up to that.
Yes, very good. So yeah, so here, let's do this in a depth first fashion. So it's going to be recursive. I mean, here the simplest way for us to think about it is that we're going to do it bottom up. But when you do it bottom up, it means that you have to have the entire search tree laid out, right? And then that would require a lot of memory. So that's not a very effective way of doing it. But we can essentially go through the tree gradually by going depth first, finding out the value here, coming back, and then backtracking like this, always just maintaining one branch. If we do that, then the complexity is not so bad. So for space, we would just need a linear amount of space with respect to the depth, because we need to just expand one branch, And then for that branch, we're going to need to essentially keep track as well of all the children of each node. So that's why it's the depth times the branching factor, because for each node in that branch, we need to remember as well which children we've already visited and which ones we still have to visit. Okay, so yeah, so space complexity is not too bad. The problem is time complexity, right? So this is not going to scale. Okay, so now what if we have more than 2 players? And here, if we have more than 2 players, we cannot have a single score where one is maximizing, one is minimizing. But a general way of dealing with multiplayer games would be as follows. You could have a score or utility that is stored in each node for each player. So here I'm going to assume that I've got 3 players, A, B, and C. So they alternate. So like in card games, for instance, you might have games where you have multiple players. Everybody takes a turn to play, right? So that's what this would look like. And now here, instead of alternating between max and min, what we're going to do is alternate between, let's say, player A simply trying to pick the move that would maximize its score, which would be the first score here in this tuple. So between 1 and -1, right? So the choice of 1 would be best. Then after that, player B would play and then choose the move that gives the second, that maximizes the second score. So here between 2 and 1, 2 is the best, so that's why we would choose that. And then for C, it will maximize the third score, and here between 6 and 3, then the best is 6, and that's why we maximize that. Okay, so that's the generalization to multiple players, and here the scores do not have to add up to 0, so it's not necessarily a zero-sum game, so this is also more general, right? So the scores could not be complete opposites. In fact, with 3 players, it's hard to have it complete opposites, but I mean, it could still be the case. Okay, any questions regarding this? Yeah?
So if, like, on the, let's say the right side, you have -1, -5, and -2, and the other side, you have 1 to 6, you will select 1 to 6, even if it's better for the overall game to select -1, -5, -2.
Ah, yeah, very good point. So yeah, so what's better for the overall game? So here it depends how the game is set up, right? So if it's a game where we've got 3 players, and the 3 players, their only goal is just to maximize their personal score, right? Then here they might not select something that maximizes the sum of the scores. In some other games that are cooperative, it would make sense perhaps to maximize the sum of the scores. But here, I guess I'm framing this as an adversarial game where nobody has any incentive to cooperate. In fact, if you want to win, you need to defeat the others. So you're trying to maximize your score and perhaps at the same time minimize the other's score. But at least here, it's really just your score that matters. Okay? All right, so as a concrete example, we can tackle the game of chess with Minimax. The problem is that in chess, if you look at the branching factor, which is the number of possible moves, it will be quite large, right? So it will be around 35. So I mean, this varies obviously at what stage we're at in the game, how many pieces are left on the board, right? But a rough estimate is that it is on the order of 35. And then how many moves or how many plies would there be before the end of the game, right? So a game could often go on for at least 100 turns. So that's why here the depth could be roughly on the order of 100. So now you see with the complexity that we discussed, right, we would have 35 to the 100, right, which is crazy, right? You can't enumerate this, you can't construct, or at least you cannot take the time to search all of that. Okay, so then an interesting question is, do we really need to look at all those nodes in this search tree? And the answer is no. So we can do something that's a little smarter. So if we're careful, we can actually prune some large parts of the search tree that is essentially suboptimal. And then for doing this, there's another approach known as alpha-beta pruning that can essentially work with the Minimax search tree and then cut off branches that are suboptimal. Okay, so this technique of alpha-beta pruning, I'm going to explain it in a moment, but it is guaranteed to return the same decision as Minimax. So there's no loss in doing the pruning here. We're only going to prune the parts of the tree that we can prove are suboptimal. Okay, so the way this works is that alpha-beta, alpha stands for the idea that when it's Max's turn, Max will try to keep track of whatever is the best value or highest value so far. Okay, so this can be thought as some sort of lower bound on Max's value, because Max is trying to come up with the highest value possible. So we're going to keep track of a lower bound that we're going to call alpha. Beta is going to be the same, but with respect to the min player. So in this case, min is trying to come up with the lowest value. So then we're going to think of this as an upper bound on the possible value for min. And then so as we're going to do the search, we're going to maintain these upper and lower bounds. And then the idea is that whenever we look at some part of the tree and then we realize that there's no way that we can essentially improve the bounds, that what we're looking at is necessarily worse because it's outside of the bounds, then we'll be able to prune. So that's the idea behind alpha-beta pruning. And then this can be quite effective, at least to reduce or prune a large part of the search tree. Okay, so let me illustrate how the algorithm works. So here I'm going to note in blue max and then in red min. And then let's say that we start and we're executing the Minimax search tree. We're searching the Minimax search tree in a depth first search. So I'm just going and first simulating one sequence of moves. And then let's say it ends up where we can earn a value of 3. Okay, so at that point, we can say that because at this level, min would try to find the lowest value possible, at this point, it has some bounds. So it knows that what it will settle on will be at most 3 because it found 3 already. So this is an upper bound. And then the minus infinity simply indicates that, well, it could get arbitrarily lower. We don't know yet. So this is a lower bound on, well, there's no lower bound, in fact, on what it might find. So right now we just have an upper bound of 3. Okay, and then for Max here has only seen as well this branch. At this point, it doesn't know yet what min is going to choose, but because here there's a lower bound of minus infinity, that's the minimum it might choose. So overall, I mean, it cannot really bound anything, so that's why the bounds are still minus infinity plus infinity. But now if we look at the next branch, so after going down this branch, then we would backtrack and look down at the next possible move here. So let's say that we can earn a value of 12. So min at this point would still choose 3 over 12 because it's trying to minimize. And then so here this would also still be without any bounds. Then we would keep going. Let's say that we see 8. So the same idea. At this point, now let's say that these are all the branches that are possible, so all the moves that are possible, then min would select 3, and that's now a precise value, so that's why the lower bound and the upper bound are the same, so 3. And then Max would know at this point that because min would select here the move of 3, then it knows that it can earn at least 3. Okay, so there might be other children where it can improve this score, but it knows that it will get at least 3. Okay, then we keep going. Now we try another branch. Let's say there's a 2 here. At this point, it means that from min's perspective, there's an upper bound of 2. And now for Max, Max would still choose this side because it knows it can earn a 3. And then on this side here, Min will choose essentially the lowest score possible. So it knows that the upper bound will be 2. And now this is interesting because you see here, we have an upper bound of 2. Here there's a lower bound of 3. Right? So basically, there's no point searching any further into this subtree because Max knows that Min will only make things worse here, and then it's just better off going with that move. So here we can prune the remaining children, and this is a case that illustrates how alpha-beta pruning can be used to essentially cut off the search. So in this subtree, there's no need to expand any more children because of this reasoning where 2 here is the upper bound, and therefore Max would necessarily choose this 3 and never consider this one. Okay, so this would keep going. Let's say we see another branch with 14. Here we'd have an upper bound of 14. At this point, Max knows that it can choose 14. So then this will revise the bound in this fashion. And then we can keep on going with, let's say, 5 here. So now it decreases to 5. So here the upper bound would be 5. And let's say 1 more, we get 2. So let's say now these are all the children. So 2 would be the precise value. And then at this point, Max would choose 3 because that's better than 2. Okay, so this illustrates how the algorithm would work. And in fact, at this point here, even if there were more branches, right, this would be cut off for the same reason as here. Okay, any questions regarding alpha-beta pruning? Okay, good. So yeah, so nothing difficult here. All right, so alpha-beta pruning does not affect the final result. So it will prune the tree, and it essentially prunes the parts that would never be used in practice. So that's the beauty of it. Now, the order in which we expand the children will affect the extent to what we can do some pruning. So bad ordering, nothing will be pruned, but in a good ordering, you can in fact reduce the complexity to b to the d divided by 2. So it's still going to be exponential, right? But I mean, it's nice if you can reduce the depth essentially by a factor of 2. So that's a huge saving, and in practice, this can help a lot. Okay, so in practice, you need to do more than just alpha-beta pruning. Often you want to also prune how deep you go, and then an evaluation function will be often useful for that. Okay, so evaluation functions are essentially functions that would return an estimate of the expected utility. So earlier I said they would go down till the end of the game and just see who wins. But then if you can evaluate who's going to win before the end of the game, then you could stop at that point, and that will reduce the search. So there's many ways in which you can construct evaluation functions. One of them is if you have domain knowledge, you can use that. But now what is more common is to in fact learn this from experience. So we're going to see next class that in the game of Go, this is essentially what happens. So there's a value function that is learned by reinforcement learning with self-play, and then so it is learned from experience. Now this value function can be expressed in various ways. A traditional way is to use a linear function, but now what's more common today is to use neural networks. Okay, so if you do this, then when should you cut the search? It depends on what state you're at. For some states that are quiescent, then they're stable, and then you could just stop at that point because nothing's going to change further. But then for other states where you expect a big change in the value, you might want to keep going deeper. The problem is that to make these decisions, often you need to have domain knowledge. Okay, so in practice, So alpha beta pruning can be effective. Now, if you do not use it, let's say that you're simply using Minimax. So with chess, then you can typically go down 5 ply. So this would be 5 alternations of 2 players playing. So it's really a depth of 10. So that's quite deep. And then that's realistically how deep you could go. And then this will get you a chess program that is, I guess, able to compete with some humans, but not very well. Now, if you want to play at the master level, then you can use alpha beta pruning. This will allow you to go deeper, so perhaps go to 10 ply. But this won't be enough to get to the grandmaster level. So for this, you need to get down to 14 ply. And then typically, because you don't want to go all the way down till the end of the game, then you need to have a pretty good evaluation function. And then for chess, what was used as well is some opening and endgame databases. So at the beginning of the game, all the moves are already predetermined in a lookup table, and same thing at the end. And then alpha beta pruning would be used simply in the middle. So at least that's how chess was tackled originally. But now what we're going to see next class is how you can essentially do all of this via reinforcement learning, and instead of using domain knowledge to define the features and perhaps some endgame database and so on, then yeah, so okay, let's stop here. I've got my signal. And yeah, next class we're going to see those interesting papers.